Let's talk about simplifying forces and moments. Imagine a metal post like this, and we have a few forces affecting it. Let's say we want to find an equivalent force and a couple moment acting at point A. So, in simple terms, we want a single force and a single moment that represents all the forces and moments affecting this post. For forces, all we need to do is break each of them into x and y components and then add it up. For moments, it's pretty much the same. We figure out the moments created by each force and then add it up. Then we can show a single resultant force and a single couple moment that accounts for all other forces. What if we can place our resultant force anywhere on the vertical post to account for the moment as well? In simple terms, we can show a single resultant force and place it somewhere on this vertical section, which will create the same couple moment we made before, because it's force times perpendicular distance. If we have an object in 3D space, the process is similar. We now express our forces in Cartesian form and then add it up. To find the moments, we use our magical equation, and then once we figure out the moments created by all the forces, we add it up. Now, let's get to some examples. Let's take a look in this problem, where we need to replace the forces and moments affecting the beam by an equivalent resultant force and a couple moment at point O. Let's start with forces. The 400 Newton force can be broken into its x and y components, so we don't need to break it into separate components. Let's add up the forces. We will back down and to the left to be positive. First, the x component. Now, the y component. Note that since we back down to be positive, the 100 Newton force, which is facing upwards, will be negative. So we can find the resultant force by finding the magnitude. We also need an angle to show the direction of the resultant force. Using tan, we can find theta, which force that take care of. Let's move into moments. Each component at the force will create a moment. Let's take a look at the x component, which is only one force. The perpendicular distance is 0.5, so we multiply the force by the distance. This will create a counterclockwise moment. Next, we look at the y components. We have two. Looking at the first force, we have a perpendicular distance of 1.5 meter. This will create a clockwise moment. Next, we look at 100 Newton force and the perpendicular distance is 4.5 meter. This will create a counterclockwise moment. Now there is one more moment that we need to keep in mind, which is given already to us. We will assume clockwise moments to be positive and add it up. So note that all the counterclockwise will be negative since we back down clockwise to be positive. And that's our answers. So, this is equivalent to this. Let's take a look at a problem involving vector analysis, same as before. We need to find an equivalent resultant force and a couple moment acting at point O. We will start with the forces first. Force F1 only has a z component, so we can write it like this in Cartesian form. Force F2 has a y component, so we can write it like this. Force F3 is already given to us in Cartesian form. Now we can find the resultant force by adding it all up. All we do is to add the I components to I components, G components to G components, and K components to K components. Next, we look at the moments created about point O by each force. So for force F1, we need a positive vector from O to where force F1 is applied. For F2, we need a positive vector from O to where F2 is applied. For F3, we need a positive vector from O to force F3 is applied. Now we can find the moment by taking the cross product. Let's start with force F1. Next, force F2. Lastly, force F3. So, to find the resultant moment, all we do is add it up, just like we did the resultant force, and this our answer. So, this is equivalent to this. Thanks for watching.